These are notes on section 8.8, which is on power series and intervals of convergence. Changing gears a little bit, we will not be finding if series converge or diverge. Instead, we're going to be finding what values of x makes a certain series converge. So a power series is defined as an infinite series that is exactly representative of the given function. An infinite series that exactly represents the given function. What we'll really be focused on today is finding an interval of convergence. So the interval of convergence is the set of all values of x for which the power series converges. So we're going to write it as an interval, and then all the values on the interval will be the values that make the series converge. The radius of convergence is how wide the interval is from its center. So we'll wind up with an interval, maybe it has a center at 5, and it goes out 2 units in each direction. So it would be going from 3 to 7. So the interval from 3 to 7 has a center at 5 and a radius of 2, the distance from the center that we go in each direction. It's called the radius of convergence. First couple examples here, just kind of to talk through the notation and terminology that we're looking at. So example 1, we actually kind of just talked about this, but state the interval of convergence if it's centered at 1 and has a radius of 4. So if we have an interval that has a center at 1, and then the radius is 4, so you're going to start at 1 and go 4 in each direction. So if I do 1 minus 4, I'm at -3, and if I'm at 1 plus 4, I'm at 5. So our interval's from 3 to 5. Now, we don't know if the interval is going to include the endpoints or not. So these could be brackets, or they could be parentheses. They could both be parentheses. One could be a bracket, one a parenthesis, and so on. But this notation would mean from -3 to 5, including -3 and also including the 5. Example 2 asks us to state the radius as well as the interval of convergence here. Most of the time we'll get down to something like this, where we have the absolute value of x minus 5 is less than, it won't always be 5, but absolute value of x minus a number or x plus a number is less than another number. In order to do that, let's first look at it this way. If we have the absolute value is less than 2, that means distance from 0 is less than 2. So x minus 5 would have to be between 2 and -2. And then if I add 5, I get x is between 7 and 3. So there's our interval of convergence is from 3 to 7, which notice would have a center at 5 and a radius of 2. So notice the center is this value right here. So when it says the absolute value of x minus something, that value is the center. Center is at C, and it's going to be as less than the radius, whatever this number is right here. That's our radius. So most of the problems that we look at will look similar to this guy here. It will give us an infinite series. So the sum is n starts at 0 and goes to infinity of 4 times the quantity x minus 3 to the n. And we are asked to find the interval of convergence. We want to know what values of x makes this series converge. So what we'll be doing is we'll be using the ratio test in order to do this. We know that this will converge if the limit as n approaches infinity of a sub n plus 1, so I'm going to replace n with n plus 1, divided by a sub n. Remember, it's the absolute value of that is less than 1. If this is true, we have a convergent series. We need to simplify what's inside here. We can cancel our 4s. I left my n off here, sorry. X minus 3 to the n plus 1, we're going to write as x minus 3 to the n times x minus 3 to the first. And these guys cancel. Limit as n goes to infinity. I no longer have anywhere to plug infinity in. So the limit as n goes to infinity, all my n's canceled, is just x minus 3. I get the absolute value of x minus 3 is less than 1. So we did the ratio test. We got down to the absolute value of x minus 3 is less than 1. This series has a center at 3 and a radius of 1. So we're going to start at 3, and we're going to add 1 and subtract 1. So we know it's from 2 to 4. Everything in between 2 and 4 makes this series converge. But we don't know about 2 or 4. So what we're going to do is we're going to check those values. So we're going to make x equal to 2, and we're going to see, does that give me a series that converges or diverges? And then we're going to check x equals 4. Let's actually check x equals 4 first, because it's a little easier. So if I check x equals 4, I'm plugging 4 in for x. So the series would look like this. The sum as n goes from 0 to infinity of 4 times 1 to the n. 4 times 1 to the n. Notice it is geometric. I have 1 to the n. But my r value is not less than 1. If you think about this series, it's just going to be 4 plus 4 plus 4 plus 4 plus 4 plus 4. Therefore, this series diverges. If x equals 4, I do not get a convergent series, so 4 should not be part of my interval, so I put a parenthesis. Check 2. This series is 4 minus 4 plus 4 minus 4 plus 4. Notice the limit as n goes to infinity does not go to 0. This also diverges. It does not converge at x equals 2. I put a parenthesis. This is the interval of convergence. If x is any value from 2 to 4, not including 2 or 4, this series would converge, which hopefully makes a little bit of sense. If x is 3.5, it would be 3 times 3 minus 3, or 3.5 minus 3, 0.5 to the n. Notice it's geometric and r is less than 1. If it's 2.5, we'd have negative 1/2. The absolute value of r is still less than 1. So that's our interval of convergence. Let's try another one. They'll get progressively a little more complicated as we go here. The sum as n goes from 1 to infinity of x to the n over n. Find the interval of convergence. We will always use the ratio test when we're looking for the interval of convergence. We want the limit as n goes to infinity of a sub n plus 1 divided by a sub n, multiplied by the reciprocal, to be less than 1. Simplify right here. X to the n times x to the first. Until you evaluate the limit as n approaches infinity, make sure you continue to write it out here. The x to the n's cancel. If I evaluate the limit as n approaches infinity, of this part, n over n plus 1, it's just 1 divided by 1, so that goes to 1. I get down to the absolute value of x is less than 1. So the limit as n approaches infinity. Degree on top's 1, degree on the bottom's 1. We divide the leading coefficients, which is just x divided by 1. So my interval has a center at 0 and a radius of 1. So my interval's from -1 to +1. And then we need to check our endpoints. If x is equal to 1, I'm putting 1 in for x. So this would be the sum, as then starts at 1 and goes to infinity, of 1 to the n. 1 to any exponent is just 1 divided by n. This is a p-series. P-series diverges. If x equals -1, and from 1 to infinity of -1 to the n over n. This is an alternating p-series where p is greater than 0. That converges. You could show it if you really wanted to think through the alternating series. Limit as n approaches infinity of 1 over n does indeed go to 0. And then as I plug in bigger numbers, 1 over 1 plus 1 over 2 plus 1 over 3, 1 over 4, notice the denominator is getting bigger every time, therefore my terms do decrease every time. So it converges at -1. So our interval is from -1 to 1, including the -1, but not the 1. The sum as n goes from 1 to infinity of -1 to the n times x plus 3 to the n over 4 to the n. Again, anytime you're looking for the interval of convergence, you're going to start with the ratio test here. So I've got x plus 3 to the n plus 1 over 4 to the n plus 1. You could include the -1 to the n if you really want to, but because we're taking absolute value, I'm going to get a positive number anyway, so I don't need to worry about that much. Divided by a sub n. It's less than 1. Simplify. X plus 3 to the n plus 1, I can write as x plus 3 to the n times x plus 3 to the first. 4 to the n plus 1 is 4 to the n times 4 to the first. And we do that, so these guys cancel. These guys cancel. I no longer have any n's that I need to think about or worry about. The limit as n approaches infinity of this is just itself. Absolute value of x plus 3 over 4 is less than 1. Multiply both sides by 4. The absolute value of x plus 3 is less than 4. My center is -3, and my radius is 4. So center at -3, radius at 4. Subtract 4 and add 4. -7 out to +1. And now we want to check. Checking x equals 1. If I plug in 1 for x, my series would be the sum as n goes from 1 to infinity of -1 to the n times 4 to the n divided by 4 to the n. Well, my 4 to the n's could cancel here. This series does not go to 0. Diverges when x is 1. If x equals -7, I would have this, -1 to the n times -4 to the n divided by 4 to the n. -1 to the n times -4 to the n. If they have the same exponent here, you can multiply their bases. It's the same thing as 4 to the n divided by 4 to the n. Canceled everything out. So this is just going to give me 1. 1 plus 1 plus 1 plus 1 plus 1 does not converge. interval of convergence is -7 to 1, not including either one. Last example problem here, example 6. The sum as n goes from 0 to infinity of -1 to the n times x to the 2n divided by the quantity 2n factorial. One other comment on this one real quick. They're all to the n. If you would have preferred to use the root test here, you could instead of the ratio test. It would get you down to the same thing. So it's still absolute value, so that would go away. Notice you get x plus 3 divided by 4 is less than 1. So it gets you to this step a little bit faster. This one you cannot use the root test, though. You've got that factorial in there. Definitely the ratio test here. Limit as n goes to infinity. Absolute value, so the -1 to the n goes away. I'm replacing n with n plus 1. So it would look like this. So that's going to be x to the 2n plus 2. Same thing on the bottom. I've got 2 times the quantity n plus 1. So it's 2n plus 2 factorial. Start to simplify. This is going to be x to the 2n times x to the second. This, I want things to start canceling out, so I'm going to do 2n plus 2, subtract 1, 2n plus 1, subtract 1, 2n. Stop there because it's going to then cancel with the 1 in the numerator. X to the 2n's gone. 2n factorials cancel. So I have the limit as n approaches infinity of x squared over 2n plus 2 times quantity 2n plus 1. Notice the degree on the bottom's 2. The degree on the top is 0. I don't have any n's on the top. As n goes not to 0, as n goes to infinity, the bottom gets infinitely big. Therefore, this whole thing becomes 0. So I get 0 is less than 1. 0 is always less than 1. No matter what I have for x, 0 is less than 1. Therefore, my interval is all real values. Any number for x, I could plug in anything for x, and this series would converge. So that's section 8.8, primarily on intervals of convergence. We'll talk about power series a little more moving forward.